All right. Good morning, everyone. So this is a continuation of your CHM 101. And the part I'm going to be taking is chemical kinetics. And my name is Taufik Ogumbayo. And we need to get to it quickly. So, okay, I'm going to be taking two parts, chemical kinetics and chemical equilibrium. But we're starting with chemical kinetics. Okay. What is actually chemical kinetics itself? We need to give a little bit of a background to what this is. We all know that when you have a reactions, or when you have several reactions, they take place at different rates. chemical reactions occur at varieties of rates. Some are very slow, some are very fast. Now, chemical kinetics deal with the study of the speed of chemical reactions or the rate of chemical reactions and also their mechanism. It's not just all about the speed, it is also by what pathway or through which pathway do this reaction occur. So chemical kinetics generally answer two questions: rate of reactions and the pathways of reactions. Now, in the course of this study, we're going to learn how to determine rates at which reaction occur. How do you express these rates mathematically? And also, what are the factors that influence this rate of reaction? What are the factors that influence this rate of reactions? Like pressure, temperature, concentrations, and catalysts. But also, we're also going to talk a little bit, that's just a little bit, about the mechanism of reaction itself. Because we can't conclude our conversations on chemical kinetics without discussing order of reaction. And order of reaction is actually one of those pathways through which you determine your mechanism of reaction. But we're not going to be getting into the detail of the mechanism itself, but we are going to introduce order of reactions and how does it relate to mechanism of reaction. Now, just like we said earlier, it has been found experimentally that rates of a reaction depends on the nature of the reacting species, temperature, concentrations of pressure. You talk about pressure when you're dealing with gases, and the presence of catalysts. These factors are important when you're talking about rate of reaction. When you change any of this, say you change temperature, you expect the rate of reaction to change. You change concentration of pressure, you expect the rate of reaction to change. If you introduce a catalyst, you expect the rate of reaction to change. And of course, the nature of the reacting species comes in when the fact that you expect different rates for different chemical species, that means the nature of those species actually play a part in the rate at which their reaction occur. Now, how does it affect the rate of reaction? When you increase temperature, it leads to an increase in the velocity of the reaction, because when you're talking about a reaction, it means you have varieties of molecules, or say you're reacting A and B. That means you have many molecules of A and B, or many particles of A and B in your reaction medium. Now, the rate at which they react together is going to be determined by temperature, because immediately you increase the temperature of the mixture, those molecules begin to gain more velocity. They begin to move faster. And when they move faster, they collide with each other more. And the fact that you are now having more collision out of increased temperature, that means you're going to have higher rate of reaction. But of course, there are many gaseous reactions which take place slowly at ordinary temperature. But when you increase the temperature, of course, they now begin to occur rapidly. Because when you increase temperature, what happens? You increase the velocity of reaction. And how do you even increase the velocity of reaction? Because the kinetic energy of those molecules increases. When their kinetic energy increases, that means they move more. When they move more, they collide more. And when they collide more, then you have more, your rate of reaction increases. Now, it has been approximately found that for every 10 degrees Celsius rise in temperature, the velocity of your reaction gets doubled. That when you increase the temperature of your reaction by 10 degrees Celsius, the velocity of reaction itself gets doubled. That is how temperature affects rate of reaction. But concentration and pressure. Now, like I said, we're going to talk about order of reaction, because we are making mention, or we're beginning to talk about order of reaction here, because you can see, with the exception of zero order reaction, as you have on your slide here, with the exception of zero order reaction. Now, what is a zero order reaction? We'll talk about that later, but just take it the way it is. For now, Now, but I can just give you a little bit of an introduction to what zero order reaction means. A reaction is a zero order reaction if a change in concentration does not affect the rate of reaction. You can have zero order reaction, first order reaction, second order reaction, third order reaction. You can even have fractional order reaction. But we're still going to be talking about zero order, first order, second order reaction, and even third order reaction down the line. But I just want you to know, when you say a reaction is zero order, what does it mean? It means that it doesn't matter what you do to the concentration, the rate of reaction will remain the same. But you will understand this more when we discuss order of reaction. Now, with the exception of zero order reaction, the rate of chemical reaction is directly proportional to the concentration or pressure of the reacting species. Now, if you have reactions in a reaction vessel, or reaction is taking place in a vessel. Now, if you have 1 molar of a reactant in a vessel, or 1 molar of A, 1 molar of B, now you now have another vessel. You have 2 molar of A, 2 molar of B. Now, what this is saying is that reaction, that vessel where you have 1 molar of A, 1 molar of B, will proceed slower than the one where you have 2 molar of A, 2 molar of B. Essentially, this is what it's saying. As the concentration reduces, the rate of reaction will also reduce. And that's what we mean when they say that, okay, the rate of reaction is directly proportional to concentration. And the same thing with pressure. But you don't talk about pressure when you're dealing with solid or solution. You talk about pressure when you're dealing with gases. If you're talking about gaseous reactants, then what that means is that the higher the pressure, the higher the rate of reaction. Now, the second line on your slide, what it's saying, it's also very important. If you have in your reaction vessel 1 molar of A, 1 molar of B in your reaction vessel, now when you start your reaction, remember you're starting with 1 molar, but as the reaction progresses, the concentration is going to reduce. Now, what that is saying is that the rate at the beginning of the reaction is not going to remain the same throughout the course of the reaction. The rate when you start, when the concentration is 1 to 1, is going to be higher, or is going to be highest throughout the course of the reaction. As the reaction progresses, concentration decreases, and therefore your rate of reaction will also decrease. And that is what we mean when we say the concentration of the reacting species do not remain constant during the course of the reaction and are continuously consumed during the course of the reaction. Therefore, concentration of the reactant decreases with time, and also the rate of reaction will also decrease with time. And that is what you're having here. This is concentration time curve. When you start your reaction for A, you can actually see that, okay, for that, you have 2 reactants here. Reactant A, which is that line, the blue line, or the blue curve. Reactant B, the red curve. And the product, the green curve. Now, when you start your reaction, you can look at where at time 0, where reactant A is starting from. Also look at reactant B, where it's starting from. Not the same concentration, but they don't have to be the same concentration anyway. But the most important thing you need to see here is that the concentration decreases in the course of the reaction. The concentration decreases. For A, it's going down as the reaction progresses. For B, it's also going down as the reaction progresses. Now, as the concentration of the reactant decreases, you can see that product starts from 0. As we consume the reactant, we produce, or we begin to get product. And the concentration of the product increases throughout the course of the reaction. Now, look at this now. This is the rate concentration curve. When concentration is equal to 0, rate is equal to 0. Because you have your, on the vertical axis, you have your rate. On the horizontal axis, you have your concentration. And you can now see that as the concentration increases, the rate of reaction also increases. We said that when we were dealing with those factors. So as the concentration increases, the rate of reaction increases. Now, we already said that the rate is highest at the beginning of the reaction. And you can see that here. That you have the highest rate at the highest concentration. You have the highest rate at the highest concentration. And remember, when you're having your reaction, you're going to have your highest concentration at the beginning of the reaction, because the concentration decreases throughout the course of the reaction. Now, but theoretically, reaction is never complete. But and we can explain the reason why it's difficult to actually get a reaction to completion. Remember that we already said that the rate of reaction increases with increase in concentration. When you begin to have reduction in concentration, the rate of reaction will decrease. You are going to have the decrease in concentration up to the point that the concentration is going to be close to, the concentration of the reactant is going to be very negligible or close to zero. And at that point, you get a point where you can hardly get anything going on. Because remember, these things have to collide with each other. And if the concentration now drops so drastically that they are close to zero, these reactants are going to be so far apart in the reaction medium that they won't even get in touch with each other. And when they don't get in touch with each other, or they are not colliding, then that means you can't even have a reaction. And that means that at the end of the day, you're still going to have some reactant present in your reaction vessel, because you can't actually get any reaction going, because the concentration is so low that those reactants cannot even get in contact with each other, not to talk of getting a reaction to take place. Now, well, we know, we already explained that the reverse is the case for the concentration of the product. As the concentration of the reactant decreases, concentration of the product increases. And I think we showed that at the beginning of the reaction. Now, this can be easily understood from, because this is that diagram that we're talking. Okay, sorry. Okay. Did I remove that now? Hold on. Sorry. Oh, okay. This is because that equation you saw now, I think I need to quickly, this equation that is rate is equal to dA minus dA dt. Now, the dA is actually talking about the change in concentration and change in time. The rate of reaction is the change in concentration with time. That is your rate of reaction. Your change in concentration with time, that is your change, that is your rate of reaction. And if you come back here, you realize that you have your concentration on the vertical axis, you have your time on the horizontal axis. If you divide the vertical by the horizontal, that will still be your dA dt, because molar concentration is going to be your dA, your time is still going to be your dt. And in this case now, that is going to give you the rate of reaction. In this case now, what we're saying is that drawing a tangent around the reactant or even around the product can actually give you the rate of reaction. We're still going to explain more about that. Now, catalyst. We've spoken about temperature. Now, catalyst. We've spoken about pressure also, because whatever happens to temperature also happens to pressure. The only difference is the fact that pressure only applies to gases. Now, you can actually have a catalyst that increases your rate of reaction or one that decreases your rate of reaction, because essentially that is what catalyst does, or that's what catalysts do. Now, but how do they do it really? How they do it is actually not our business in CHM 101, but we can't just go ahead and just be like, because I know students like asking why. or how. The real thing, or what happens there, is more often than not, catalysts change the pathway. Remember, we said chemical kinetics is about mechanism of reaction, and mechanism is about pathways through which a reaction takes place. What catalyst does is that it changes the pathways to a shorter one or to a lower energy one. If the original reactant, say it's going to take it's going to take a longer path, when you introduce a catalyst gets involved in the reaction and create a shorter pathway for that reaction to take place. Or that is the one that increases the rate of reaction. The one that decreases the rate of reaction will introduce a longer pathway. Now, for example, when you have hydrogen and oxygen, they are not just going to combine without a catalyst. H2 and O2, hydrogen, oxygen, they don't just, you can't just have the two together and you expect them to react, really. Because the reaction is like, it's not the kind of thing you kind of like expect to be spontaneous. So, but if you introduce a platinum or a platinum catalyst, they combine and the reaction is very rapid. Now we're talking about a reaction that doesn't even take place at all. And even if it does, because there are times when we say, okay, reaction doesn't take place. It doesn't mean there's no reaction. It's just too slow to observe. And that's why sometimes I like to use gold and water. That, okay, who says there's no reaction at all? But it's just too slow that the kind of reaction that is taking place, for you to even observe anything is taking, it might take 1,000,000 years. So, but again, it doesn't mean that you can have a reaction if you introduce the catalyst. And it's the same thing here. H2O2, you won't notice any reaction, but introduce a catalyst, you have a very rapid reaction taking place. Now, another one is okay, sorry, I need to quickly shut this. Okay. So, a small amount of glycerin or acetanilide, they also slow down the composition of hydrogen peroxide. Normally, the composition of hydrogen peroxide is rapid, but this is the first one now, which is platinum in the H2 and O2, or hydrogen and oxygen in the presence of a platinum catalyst. That is a situation whereby a catalyst increases the rate of reaction. The second one is glycerin or acetanilide. If you add it to hydrogen peroxide, it decreases the rate of reaction. And when you have a reaction that takes place in the presence of a catalyst, they are known as catalyzed reaction. We refer to those ones without the catalyst as uncatalyzed. Now, the rate of reaction, we've been talking about the rate. I'm sure that you know it's an intuitive thing. When we talk about rates, we kind of like have an idea of what the rate of reaction means. Okay, one is fast, one is slow. We kind of like have an idea. But we need to have beyond an idea to be able to make use of them the way we want to use them here. We need to have a clearly defined way or of determining what our rate is. And if we need to have a clearly defined way of determining our rate, then we need to have a very clear or lucid understanding of what rate is, beyond just an idea. Now, we already said that the rate of a chemical reaction is defined exactly the same way as we define the speed of a moving object. Because remember, if the car is moving, you can talk about its speed. That is, how long does it take for this particular car to cover 1 kilometer? You want to determine that. That means, okay, if it covers 10 kilometers, you need to determine the amount of time it took that particular car to cover 10 kilometers. Then you divide the number of that kilometer by the amount of time. And this is what we mean by speed. Distance traveled divided by the time required for that travel. Which is the same thing as change in position divided by the time required for that change. What this is saying is that it's not just about car. We can talk about the rate of change of anything or the speed of change of anything. So rate of reaction is also the speed of reaction. Rate of reaction itself is the speed of reaction, which is also the rate of change with time. And we're talking about the rate of change of reactant to product with time. Now, but because we measure concentrations in mole per liter or mole per dm cube, just like we measure distance in kilometer, we are just going to be dividing the concentration by time. And if we're dividing the concentration by time, remember, for speed of a car, we use kilometer per hour. While for rate of reaction, since we are dividing concentration by time, it's going to be mole per liter per second, because the unit of concentration is mole per liter, while the unit of time is in seconds. Then you're going to have mole per liter per second. More often than not, that's what we use. Now, let's now look at an example. Okay, just a minute. I just wanted to be sure that the people on YouTube are seeing what, okay, that's fine. Okay, so we can continue. Okay, now look at this reaction, which is the decomposition of gaseous nitrogen pentoxide to give you nitrogen 4 oxide and oxygen. Now, you can determine the rate of reaction by measuring the increase in the molar concentration of O2 in a given interval, meaning that if you have your nitrogen pentoxide in a reaction vessel, you can measure the reduction. You can, because there are two ways to do this. In fact, maybe there are three ways to do this. But the best way to do this is to measure the oxygen. But there are two ways. You can look at the reduction in the concentration of N2O5, or you can look at the increase in the concentration of oxygen or nitrogen 4 oxide. But let's say we want to use oxygen. Now, remember, you're going to have your initial concentration of oxygen, which is going to be 0 here, because at the beginning of the reaction, there will not be any oxygen in that reaction vessel. Or, well, in your product vessel, because this kind of reaction, you won't have any oxygen. But at the end of the reaction, there will be oxygen. Now, what you do normally is to continue to monitor the concentration of oxygen in that reaction vessel. So what you do is you subtract the initial concentration of oxygen from the final concentration of oxygen, because that will give you the amount of oxygen produced in the course of the reaction. Now, the reason why people will just write it this way and will just not be like, okay, it's 0. It's okay. Since oxygen is present everywhere, what of even if you have oxygen as some oxygen even before the commencement of the reaction, meaning that you should be able to detect that oxygen and subtract it from what the total oxygen is going to be at the end. But in this case, we want to assume that there is no oxygen. You already make your reaction vessel oxygen free before the commencement of the reaction. And if there is oxygen, make sure that you measure. That means you want to measure your reactant at the beginning of the reaction. You want to know the concentration. You also want to know the concentration of all the products at the beginning of the reaction, even if they are still going to be 0. So that after some time, because when you're determining the rate of reaction, after some time, you can now look at, you need to note that time, and you also need to know, the amount of oxygen produced, which you will get by subtracting the initial amount from the final amount of oxygen. And that will give you the change in oxygen concentration in the course of that reaction, which is your delta O2 here. Now, the time required for the change, remember, is the rate of change with time. The time required for is also going to be the final time and the initial time. The initial time is going to be 0 anyway, more often than not. There's a reason why they write it to T2 minus T1, and they're just not saying time. But for now, just assume that your T1 is equal to 0, while your T2 is going to be the time at which you conclude the reaction. Now, the rate of reaction now So your rate of reaction now will now be, the rate of formation of oxygen is now going to be O2 divided by, or change in the concentration of oxygen divided by change in time. And like I said earlier, instead of using oxygen, you can use your N2O5. But in this case now, you need to take okay, there's something I forgot to say. You can see that we have a negative for your N2O5, there is a negative. There is a negative. The reason why and for oxygen, there is no negative. This is the convention. And the reason why you have that as the convention is that, remember, for reactant, there is going to be a decrease in concentration. And that's why you have that negative, telling you that there's going to be decrease in concentration in the course of the reaction. While for the product, there is not going to, you are going to have an increase in concentration, and that's why you have a positive for product. So, and that's why the negative sign is important. Because remember that for reactant, if you subtract the initial from the final, you're going to have a negative sign. Because the initial concentration is going to be higher than the final concentration. And that's why you have that in brackets there. The final concentration of the reactant minus initial concentration is going to be a negative. While for product, the final concentration minus initial is going to give you a positive. The concentration of reactant decreases with time, decreases with time. That's why it's negative. That of product increases with time. That's why it's positive. Now, we already spoke about the unit of rate of reaction. We already spoke about the unit of rate of reaction. Okay, sorry, because I need to check YouTube to make sure that because somebody told me they kind of like had a disconnection. So, okay, the streaming on YouTube is because if we are going to have more students, because I think we have around 1,000 students on YouTube now. So if you're going to have more students on YouTube, then is it 1,000 on YouTube? So we need to also make sure that it's running so that we don't just keep talking why they can't even hear what we're saying. Now, okay, so we already spoke about the unit of rate of reaction, that unit of any parameter originates from the mathematical formula for that particular parameter. In this case, we're talking about rate, and rate is concentration divided by, or shall I say, change in concentration divided by change in time, or divided by time. And since we express concentration in mole per liter, and we express time in seconds, whatever it is, even if it's a minute or hour, the most important thing is that you're going to have your mole per liter by your time unit, be it second, minute, or hour. And that's why you have mole per liter per second, mole per liter per minute. There's supposed to be a slash between mole per liter and second and those times. I'm not sure why those slash are missing. Please take note of that. And because it's not mole per liter second, it's mole per liter. Oh, okay, sorry. I think it's correct. It's correct, really. I understand the reason why it's written this way, because you're still going to have the second as your denominator. Because if you want to write this, it's going to be mole divided by liter multiplied by second. That's the way it is. So that still makes sense. So it's still correct, please. There was something, I had something else in my head. So all those things are still correct. There's nothing to change. And don't worry, we're still going to have, I normally leave 10 minutes at the end of the class for your questions. So we're going to stop the class at 9:50 so that we can take questions for 10 minutes. So please relax. If you have any questions, you're still going to have the time to ask your questions. So now, but again, there's something important here that we need to call our attention to, which is if you look at this very well, the number of moles of reactants, the mole ratios are different. You have 2 mole of reactants, 4 mole of NO2, and 1 mole of oxygen. Now, the question is, how does this affect our rate? Because this is definitely going to have an effect on how we calculate our rate. And we'll explain why this is so. Now, from this equation, you have 2 moles of N2O5 required to produce 1 mole of oxygen. In other words, that means the rate of decomposition of N2O5 is twice as fast as the rate of formation of O2. Because that means you need, please make sure you understand this very well. To produce 1 mole of oxygen, you need to decompose 2 mole of nitrogen pentoxide. Now, what that means is that the rate at which you decompose nitrogen pentoxide is twice as fast as the rate at which you're forming O2. Now, that means that, because the reason why we use O2 the other time is that, okay, you have 1 mole there. And at the end of the day, the rate has to be, they must be equal to each other. You can't say the rate at which I'm doing one is different from the rate at which, yeah, well, it's not impossible, but if you want to talk about the rate of this reaction, then you should be able to use any of the reactants or any of the products. And that is why there has to be this reading, or there has to be an agreement between them. Now, for you to be able to equate this expression, or for you to be able to equate this, remember, we already said that the rate at which you produce your oxygen is half the rate at which you're decomposing your N2O5. And that has to be reflected in that equation. So if you want to represent your rate of reaction using all of this, or you want to compare, you want to equate the rate of decomposition of N2O5 to the rate of production of O2, then that too has to be reflected. And that is why you now have, if you're using N2O5, that means you're going to divide it by 2. Meaning half N2O5 divided by time is equal to O2 divided by time. So those number of moles, they become important when you're talking about rate of reaction. They're not just things you can ignore. It is easy for oxygen because it's just 1 mole. Now, if you want to equate anything to oxygen, then the number of moles has to be taken into consideration. It's the same thing here for nitrogen 4 oxide, because at the end of the day, the rate at which you produce nitrogen 4 oxide quadruple the rate at which you produce oxygen. By the time you produce 1 mole of oxygen, you already produce 4 mole of NO2. That is telling you that the rate at which you're producing NO2 is faster than the rate at which you're producing O2. Like I said, you now need to equate the two. To equate the two, that means the rate at which you're producing your oxygen equals the rate at which you're producing NO2 divided by 4. Now, let's now look at a typical set of data Okay, now there's something that I need to say. What I'm going to do is while I was preparing this, maybe I left that out. Okay. Now, what I'm going to, okay, I won't be able to do what I wanted to do. I won't be able to enter because we already have 300 students. Since we already have 300 students, I'm not going to be able to enter. I wanted to bring in, because I thought I would be able to write, because normally I have a writing gadget, but I'm going to have to connect. For me to be able to do that, I have to connect the iPad. I forgot to connect it really, because I thought I was going to be able to write. But now I can't enter again. So we're just going to have to, or maybe next class, I can just find a way to do that. Now, there's something called average rate of reaction and instantaneous rate of reaction. Because if you look at this table, while we were trying to cut short our slide, I think we removed almost everything I found important, but we needed to remove some of those things so that we can actually compress the slide. But again, we find ourselves there. Now, there's an average rate of reaction and there is an instantaneous rate of reaction. These two are very important. Now, remember that when we started, there was something we mentioned. We are still going to talk about the table and the data here, really. Now, what we said was that when you start your reaction, as the reaction progresses, concentration decreases. And as the concentration decreases, the rate of reaction decreases. Now, that means if we come to this, curve, now the rate at the beginning of this reaction, at the beginning of this reaction, it's not going to be the same rate in the middle of the reaction. Just like it's not going to be the same rate at the end of the reaction, because the concentration keeps changing. And that is why this curve, that is why when you want to, the rate concentration curve is never a straight line. Look at this. That's why this is not a straight line. You see that they didn't draw this as a straight line passing through the origin. No, it is a curve. What this is telling you is that at different concentration, the rates are different. If they were the same, you will have a straight curve. Remember, if you want to measure the slope of a straight line, the slope at every point on that line will be the same. And that is telling you that the rate of reaction at every point on that line remains the same. But in this case, you have a curve. If you want to, you cannot just find that, well, you can talk about the general slope, but again, at every point on this curve, the slope are going to be different. That is why it's not a straight line. That's why it's a curve. And remember, the slope is telling you, because it's actually reflecting that okay, at every point here, the rate relationship data is not a straight line relationship. It's not a linear relationship. Almost, but not, because you get a curve. Now, that is what takes us to what average rate and instantaneous rate is. You see, if you measure your concentration at the beginning of this reaction, say you come here, you measure your concentration at the beginning of the reaction, and you measure your concentration at the end of the reaction, and you subtract your concentration at the end from the, your concentration at the beginning from your concentration at the end, and you divide by time, that is going to be an average rate of that reaction. Because on this curve, those rates are different. What you're going to get is just going to be an average rate of reaction. But if you draw a tangent around a particular point here, say you come very close and you draw a tangent. Say you come very close to the beginning, because there's also something called the initial rate of reaction. The initial rate of reaction is a form of instantaneous rate of reaction. Instantaneous because you're measuring at an instant, at a particular point. Initial because that point is at the beginning of the reaction. Because remember, initial is the beginning. So you're measuring at the beginning or at any point. If it's an instantaneous rate, you want to measure at a particular point. You draw a tangent around a particular point. If it's an initial rate of reaction, which is also an instantaneous rate of reaction, you must go to the beginning of that reaction and draw your tangent to get your rate. That is what they mean on that table when you have your, where you have your average rate and instantaneous rate of reaction. Now, the thing here is that we didn't talk about the point at which the instantaneous rate we're taking. We're still going to talk a little bit more on that when we get to order of reaction. But the most important here is to pay attention to the average rate of reaction. But please understand what instantaneous rate of reaction is, understand what initial rate of reaction is, and then also average rate of reaction. Now, if you look at this time in second, this is the concentration. Now, when you're starting your reaction at 0 time, you're starting at 2.33 mole per liter. Then after 184 seconds, the concentration is 2.07 per liter. Now, to determine this average rate, what you're going to do is you're going to subtract. Remember, we said the initial concentration minus the final concentration divided by your time, meaning that 2.07 minus 2.33 divided by 184. Then you want to go to 319, then you do the same thing. That is the rate there, the average rate at that particular point. And again, you will realize that the average rate decreases. Because when you get to the second point, what do you want to do? This is what I call the initial rate anyway. But when you get to the second rate, which is 319, you still start from your 0. You subtract 2.33 from 1.91 and divide by 319 to give you the average rate. You now realize that the average rate for the second one is lower than the first average rate. And why is that? We already said that the lower the concentration, the lower the rate of reaction. Now, the original average rate was higher because that was determined at higher concentration. Now you've added lower concentration into the mix here. Because now you're dealing in at lower concentrations, that reduces the average rate further. And you can see that as we go down, the average rate also decreases. Now, hold on. Okay, it's still there. So now this is just telling you how we arrive at those. Now this is telling you, for example, the average reaction rate between 319 seconds and 529 seconds, the decomposition of N2 decreased from 191 to yeah, that's correct. Really, I think I made a mistake. You're not starting from 0 again because you are just looking at average rate for that interval. Average rate for that interval. So now, if you look at our 319 seconds and 529 seconds, 319 seconds and 529 seconds, so you have 1.91 and 1.618. That means you're going to be subtracting 1.91 from 1.68. So this is, and now the time also, which is what time now? Okay, sorry. This is 529 and 319. Not. I think there's a mistake here. Not 5.29, or no, this is 529 minus 319, not 5.29. And so you have this answer. So now, we already spoke about it a little bit, that the instantaneous rate of reaction is the rate at any specific instant time. Now, when the variation in concentration of a reactant or product with time is plotted, the slope, I think I already explained all this. Now, the instantaneous reaction rate at T is equal to 0. The instant when the reaction begins is called the initial reaction rate. All these are already explained. Now, all these also we already explained, talking about the relationship when you want to determine your rate, and when you have your, in this case now, we already spoke about that under our nitrogen pentoxide. You can see this is 1 mole. That is, hydrogen is 1 mole. Iodine is also 1 mole. Hydrogen iodide is 2 mole. You can equate this to each other, but if you want to now add hydrogen iodide, that means you're going to have to divide by 2, meaning that this is going to be minus H2 divided by T is equal to minus iodine divided by T is equal to minus iodine divided by T divided by 2, which is, okay, that is not there, but that is what it should be. I'm just saying. Now, we now have an example to deal with. But before our example, okay, let's do this example first. So before I take your question, I'm asking myself, will I have enough time to, but let's do the example. Now, okay, at some time it was observed that in the reaction, the rate of formation of NO2 was 0.0072 mole per liter per second. Now, what is the rate of change of O2 in mole per liter per second at this time? That is A. Then B, what is the rate of change of N2O2 in mole per liter per second at this time? Then what is the rate of reaction at this time? Now, you've been given this rate. And remember what we said. Hold on. Okay, we're calculating for oxygen first. Okay, and we're given for NO2. Good. So now remember what we said, that means the rate at which you produce your NO2 is quadruple the rate at which you produce your oxygen. Quadruple the rate at which you produce your oxygen. Because what this means is that 4 mole of oxygen, 4 mole of NO2 and 1 mole of oxygen. Now, and that's why to balance that equation, it means that 1 mole of oxygen divided by, the balance equation gives the reaction rate, which is 1 mole of oxygen divided by 4 mole of NO2. Now, what that means is that your rate of production of oxygen is going to be the rate of production of NO2 divided by 4. Because you see, we need to think about this logically before we come to the mathematical equation itself. If we're saying that the rate at which you're producing your NO2 is 4 times the rate at which you're producing your oxygen, and you're given the rate at which you're producing your NO2, and you're asked to find the rate at which you're producing your oxygen, that means you're going to divide the rate at which you're producing your NO2 by 4 to get the rate at which you're producing your oxygen. And that is exactly what we did here. Because at the end of the day, 1 mole of oxygen gives you 4 mole of NO2. And you can now multiply that by the rate of NO2. Essentially, you're dividing the rate of production of NO2 by 4. Now, the second part of that question says that N2O5. What is the rate of change of N2O5? Now, the rate at which you're producing your NO2 doubles the rate at which you're decomposing your N2O5. Meaning that if you want to determine the rate at which you're producing your N2O5 from the rate at which you're producing your NO2, that means you need to divide the rate at which you're producing your NO2 also by 2. Because I want you to understand this very well, not just all about, oh, what is the formula? That you must understand this beyond the formula. What is the logic behind that? And that is what we have, and that's what we have here. 2 mole of NO2 to give you 4 mole of, 2 mole of N2O5 to give you 4 mole of NO2. Then that will be 1 mole to give you 2 moles. And eventually, you're going to be dividing by 2, essentially, to give you 0.0036 mole per liter per second. And now we can calculate. We can calculate the rate of reaction, because the rate of reaction is always per mole. Really, it's always per mole per liter. And if it is per mole per liter, That means even for oxygen, from this equation, the rate, because for every one of them, it has to be the same thing. It doesn't matter which one we're using. We can use N2O5 to calculate. We can use NO2 to calculate. We can use O2. But if we're using O2, we're not going to, because we already have 1 mole of O2. So what is the rate of producing 1 mole of O2? It is going to be 0.0018. Then what is the rate of producing 1 mole of NO2 also? What is the rate of producing N2O5? It's going to be 0.0018, because all you need to do is divide its the rate of its production, which is, where is it now? We got 0.0036 here. 0.0036. And if you look at the question, we have 2 moles. That means we're dividing that 0 point, because this rate you're seeing here is for 2 moles of N2O5. How long will it take? Or what will be the rate for? Because you need to write it. So now that's why you're dividing by 2. For NO2, we're given the rate at which you're producing your NO2 here, which is 0.0072. But it is 4 moles. This is producing 4 moles. So what will be for our 1 mole? You're also going to be dividing by 4. And that's why you also have this also done. But at the end of the day, everything must be the same. It doesn't matter from what angle you're calculating. 0.0018, 0.0018, 42. And even oxygen itself is also 0.0018, since that one is already in 1 mole. Now, that's where we're going to stop. We're going to go to rate law next class. Now, I want to take questions. So raise up your hand if you have any question. Please raise up your hand if you have questions. Afolabi, okay, Afolabi, you can unmute.
Okay, sir. Thank you, sir.
Yeah.
Yes, sir, I want you to help re-explain the part where you distinguish between average rate, instantaneous rate, and initial rate. The difference between the 3, sir.
Okay. Average rate and okay, sorry, because I want to take all the questions at once. Average rate, instantaneous rate. Okay. Victor Godwin, you can unmute now.
Okay, sir. I want to ask, what if either one of the reactant or the products is a solid? Then it will not be possible for we to express the rate of reaction in mole per liter per second, because you cannot express the this in concentration of the solid in mole per liter. So what this in units are we going to use then?
Okay, thank you. Then Joshua Anyao, okay, please mute yourself back. Joshua Anyao, you can unmute now.
Okay, sir. Yes, sir. So my question is, when you give the first example of the decomposition of oxide, when you're talking about, I think when you were answering the question, I was confused at the point when the rate of reaction of, for example, O2, how the initial and the final minus initial, I don't understand that part. So, okay, I don't know if it gets, like, if you can come again with that point of T2 minus T1 of the rate of reaction.
Okay, all right. Now, okay, unmute yourself. Mute yourself, please. Great test. Unmute yourself, please. And then I'll be, okay. That'll be the last question I'll take.
Sir, please, when we are done, please, can we get this slide?
Oh, definitely, you get the slide.
Okay, sir.
Okay, so I can still take the next question if that's just what you wanted to say. So, Camila Ibrahim, unmute yourself, please. That will be the last question.
Okay, sir. Please, could you come again with the calculations? Because you say it's not all about understanding the formula, that we need to understand the concept. So the second example that you gave us, please, sir, could you come again with the calculations?
Okay. All right. Calculation example. Okay, thank you all. Okay, so I'll take those questions. Now, okay, I'll first take if the reactant is solid. Now, okay, why there are solid state reactions, which is very rare, really. It's not like we don't have solid state reactions. I'm taking, don't worry, the one that, the question on average and instantaneous, I'm coming. I just want to, the simpler the questions, the easier it's going to be to explain. Now, you see, we are not talking about, your reactions are in solutions here. In fact, most reactions, remember, if you want to conduct any reaction in the lab, what do you first do? You dissolve, you try to make a solution of your reaction. I'm not saying that there are solid state reactions, but what we're talking about here, we're not talking about solid state reaction. We're talking about your reaction in solution on gaseous form. And at the end of the day, if it's in liquid form, you're going to be able to talk about it in mole per liter. So we're not referring to any reaction in solid state. So I think that's that. Now, the average and instantaneous rate of reaction. Let's go back to this to be able to talk about that. Now, you see, average and instantaneous rate. What's going on? Why is this one now giving me attitude? Okay. Sorry. So now, what we said on that was that the concentration of the reaction decreases as reaction progresses. That means that, and we already said, rate is proportional to concentration, meaning that as the concentration decreases, the rate of reaction also decreases. Now, that means that your rate of reaction will not stay the same in the course of the reaction. When you are starting your reaction, say you're doing 2 molar, your reactants are 1 molar. When you're starting out with your reaction, you have 1 molar. That means the rate at that point is going to be higher than, say, when you now get to 1.5 molar, then the rate at that point is also going to be lower than, it's also going to be higher than when you get to 1.11 molar. If you're starting from 2 molar, when you get to 1.5, of course, the rate is not going to be the same as when you started from 2. When you get to 1 molar, the rate is also not going to be the same as when you were in 1.5. In the same reaction vessel. So in the same reaction, the rate will not stay the same throughout the reaction. It decreases as the reaction progresses. And which is one of the reasons why reaction hardly goes into completion. Now, we're now saying that because of that, you can't measure rate at the beginning of the reaction and tell me that is the rate of that reaction throughout. No. You need to tell us what kind of rate are you measuring. If you're measuring instantaneous rate of reaction, you will tell me, oh, this is an instantaneous rate of reaction at so time or at what concentration. So that is what it means by instantaneous rate of reaction. You're telling me if you are starting with 2 molar and at 1.5 molar you want to measure your rate, you have to tell me that I measure that rate at 1.4 molar. That is the instant at which you measure that rate of reaction. But the average rate is throughout the whole reaction. It doesn't matter what the rates are in between. What is the rate from the beginning to the end? That is going to cover the average for that time interval. It doesn't matter. You can specify the time interval. Oh, from 0 to 15 seconds, the average rate is this. From 0 to so, the average rate is this. Nobody cares what the rate is when it was 5 seconds, when it is 10 seconds. No, nobody cares. They just want to know, at what rate did you produce this? But they also know that the rate will vary in the middle. That is what we mean when we say an average rate, instantaneous rate. And I also said that there is an initial rate, which is at a particular point. Also, but that point is at the beginning of the reaction. When you want to measure, initial rate, you see it's an instantaneous rate that you measure at the beginning of the reaction. You measure at time 0, close to time 0. Your tangent must start time 0. So that is the difference between average rate, instantaneous rate, and initial rate, which is also a form of instantaneous rate. Now, the N205, the final and initial that your questions was on. Oh, where is it now? Now, you see, at the end of the day, when you have we had where is it? Okay. You have reactants, you have product. But you can determine your rate using any of this. You can use your reactant, you can use your product. But the convention is that when you're writing for reactant, when you're writing the rate for reactant, you can see that we have a negative there. The reason being that when the convention is to subtract the initial concentration from the final concentration. And the final concentration, and the initial concentration for the reactant is always going to be, is higher than the final concentration of the reactant because it gets consumed throughout the reaction. Because if you come back here again, the beginning here is going to be our initial concentration of reactant A, while the middle here is going to be wherever you want to call your final, or if we want to go to the end, that's going to be our final. And if you subtract your initial from your final, you're going to end up with a negative sign. While for the product, the initial is going to be lower than the final, because for a product at the initial stage, you don't even expect to have anything. You expect it to be zero. And at the final, you expect to have something substantial. So you're subtracting the final, the initial from the final, and that is going to give you a positive sign. And that is why you write for oxygen, there's no negative, there's positive. Because you produce more oxygen. You produce oxygen. You see, at the end of that process, you are going to have oxygen. Your oxygen is going to be positive at the end of that process, while your reactant is going to be negative at the end of that process, if you can look at it from that angle. That is that. Then the calculation, because I don't like, and I want to believe that you have another class after this, so I don't like to delay students. But because you asked the question, and I'd like to take them. So the last question, which is, where is it now? You're talking about this example. I want to believe that you're talking about this example. The concept itself. Now, I'm sure you're asking about the concept. Now, what I said was that, you see, you want to determine the rate of reaction, and you can use any of these individual species. You can use N2O5, which is a reactant. You can use NO2, which is a product. You can use O2, which is also a product. But the thing here is that the number of moles are not the same. And you must arrive at the same answer, irrespective of whichever one you're using. Now, the only way you can actually arrive at the same answer is that, you see, the rate has to deal with a mole of any of this. Because what you're going to get, if you're calculating for N2O2, you'll get a rate, just like we have here. The rate of formation of NO2 was 0.0072. Now, that is the rate of formation of 4 mole of NO2. That is the rate of formation of 4 mole of NO2. But what you want is the rate of formation of 1 mole of NO2. The rate of formation of O2 is going to be for 1 mole. Why the rate of formation of this is also going to be for N2O5 is going to be for 2 mole. So, but like I said, at the end of the day, they must be equal. We were given rate of formation of NO2 to be 0.0072. But what did we call what did we arrive at as the rate of reaction? 0.0018. How did we get there? We have to take this 4 into consideration. That this 0.002 was for 4 mole of NO2. To get 1 mole of NO2 would only take what? That would be what as the rate. And that's why we divide by 4. You want to do for, if they're using N2O5, you divide by 2. So I'll stop, and I think that's the answer for, that's the explanation for that. So we'll stop the class so that you can attend your next class. So I'll see you on Wednesday. By God's grace. Good morning. ẹ̀rọ tó mi wà ní borí kọlẹ̀ mo ti máa wọ́n tó torí ẹ̀ ń pè mí anyway. ṣé lẹ́tà yẹn ṣé lẹ́tà gan ti dá ṣé lẹ́tà dé láti PG school because lẹ́tà yẹn ò tí ì dé láti PG school HOD rẹ̀ rẹ̀ HOD máa sọ pé tí wọ́n bá ti mú lẹ́tà wá because mo ti try láti ipò mo try láti pè wọ́n ganjọ́ tí mo kọ́kọ́ gbọ́ professor fashion ti kọ́kọ́ sọ fún mi but HOD máa sọ pé tí lẹ́tà ò bá dé because so even ọjọ́ ìmúdíkà kí n lọ bá mi wo PG note mi pé ṣé lẹ́tà yẹn ti wà ní PG note mi wọn ò dẹ̀ rí ìwọ gan lọ sí ọ́fíìsì bí èmi máa wà ráhùn lọ́la náà bí wọ́n bá dẹ̀ rí lónìí náà kò sí nǹkan tí màá ṣe sí lónìí náà nítorí mi ò sí ní school but we need that letter fẹ́ mi dẹ̀ ń bọ̀ lọ́la ó dẹ̀ lọ bá wọn bẹ̀ bóyá láti bọ̀ because wọ́n ká fún wọn lẹ̀ jà èyí tó yẹ kí lẹ́tà ọjọ́ náà ti sọ lè ní tí òun ẹgbẹ́ lẹ́tà yẹn lọ sí. Wọ́n ti rí payment ẹ̀ irọ́ ọjọ́ bá ti rí wọ́n lè má process ẹ o. ó mọ̀ nǹkan ló ṣẹlẹ̀ jẹ́ ká ti ẹ̀kọ́ òwò ṣe lẹ́tà ní sùúrù jẹ́ ká kọ́ òwò ṣe lẹ́tà ti dé lọ sọ́fíìsì HOD kò ní mo ní sọ pé mo ní kọ́ bá mi sọ fún kí ló ń borúkọ ẹ̀ Mr. Ọlá pé kọ́ bá mi wo PG note mi ṣé lẹ́tà ọ̀kan wá láti PG school síbẹ̀. No because no ká tó máa sọ pé ká tó máa sọ̀rọ̀ ká ti ọ̀kọ́ ká ọkọ́ check yẹn náà. Oh, okay, mi ò pé torí kíní lo ẹ̀wọ̀n òkè yóò yẹ ká ti dóòmù tẹ̀ ti táì fọ́ọ̀mù ẹ̀gàn náà ẹ̀mú ti táì fún kíní ẹ̀gàn tán kọ́kàn ti ẹ̀jẹ̀ kọ́ fún wa ní kárí lẹ́tà ká lè mọ kámọ̀kó wà official ni. No, ó dọ̀là. No, ó dọ̀là. Màá wà ráhùn lọ́la. Mo ti wò HOD sí àrùn last week rárá. No one. Okay. Okay. No one. Lọ wo bẹ̀ because ká tẹ̀ ọkọ mọ̀ ni. All right.